Good morning, all of you. First of all, I will like to thanks all participants to take uh, participation in the 1 week faculty development program, and I want to take moment to appreciate each one of you for your active participation, enthusiasm, and dedication for the past 3 days. Your energy and communication commitment and truly made this FDP meaningful and engaging. Anushka, I would like to thank all participants, attendees, and our resource person, Mr. Prashant sir. So, shall we start today, Prashant sir?
Yes, we can start. I'll share my screen. Let me know once you are able to see it, and I can get going. Uh,
Yes, sir.
is it visible? No.
No, sir.
Okay. So, okay. Okay.
Now it's visible, sir.
All right. Thank you. Okay. So let's start with the fourth lecture. So in the first one, we covered introduction to ML. Second one, second and third we covered supervised machine learning. So uh, where in the second lecture we covered linear and logistic regression, which are basically linear models, and third lecture we covered decision trees. We covered a clustering algorithm, k nearest neighbors, and we also covered support vector machines. So we kind of broadly covered all the basic shallow machine learning, supervised machine learning algorithms. So now today we are going to go to unsupervised machine learning. So, on the first day, we discussed what unsupervised machine learning is, where in case of supervised machine learning, you have your features. So, for example, let's say x1, x2, x3 are your features. Features are nothing but your column names, right? Like the name of your, like in an Excel sheet, your column is the feature, and y, let's say it's called a target, right? Let's say it's called y. Y is what you're trying to predict using x1, x2, and x3. You're trying to predict y, right? And if you have all this data with you, say you have 100 such data points with you, you use these data points with x1, x2, x3, and y. You tell the model, okay, if x1 is this, x2 is this, and x3 is this, then y should be this. Okay, then you train the model using these 100 data points so that it learns the pattern behind how x1, x2, and x3 are related to y, right? And that is, and then when you give any extra point, your 101th point that you give to this trained model, the model should be able to predict the value of y. That is your supervised learning problem, where you, in your training data, you had the target label with you. Now, how does it differ from unsupervised learning? It In case of unsupervised machine learning, you do not have a target. So you don't have a y in this case. You just have x1, x2, and x3. You don't have a y with you. So then how would you predict? Like, what are you trying to predict, right? You don't know what you're trying to predict. So the thing is, you have a bunch of information and you're trying to make sense out of the information. So let me give you an example. Let's say this plot is like, I have a set of 15 people, right? Let's say each node is one person, and I have a set of 15 people. Each of them belongs to some country. Okay, they have some nationality, they belong to some country, and all of them belong to one of three countries. Let's say country A, country B, and country C. Now, we don't know which person belongs to which country. Okay, but we have some kind of information about each individual. So, by what do I mean by this? We have some kind of information, as in we might have age of the person, age of each of these people, 15 people. You might have weight, you might have skin color, you might have medical condition, or some data, right? You might have some uh, 20 different features of each of these individual that you see in this data set, right? So now, using this information, I want to I want to cluster the people together such that I could form three distinct clusters, and then I could say that, okay, maybe these. So after I run my unsupervised machine learning algorithm, I found that these people are clustering together, these people are clustering together, and these people are clustering together. So maybe all of them who are in the same cluster belong to one country, right? So this is a classic example of how you could use unsupervised machine learning, where you don't really know what labels are there, and you are just trying to make sense of the data, right? So the first algorithm that we are trying to explore, that we'll try to explore in unsupervised machine learning, is called principal component analysis, right? It's also called PCA commonly. So PCA is nothing but the same thing what I said earlier. So you have a bunch of data points, and what you're trying to do is you're trying to cluster them together to see which of them belong to the same class, how each of them can fit in together, right? So to start with, I will give an intuitive overview of PCA, and then from there we'll go a little bit into the math. But let's start with an intuition of how PCA will work, right? So over here, as you can see, we have an image which has like some nodes in it. Let's say it's a data set of cells, right? It's a data set of cells from a certain tissue in a person's body, right? Now, each of them could be different, or they could be the same. So each of these cell could be the same type of cell, or they could be different types of cells. Now, this group may contain three different cells, cell types. So the problem is that this tissue, we see a cluster of cells over here, but some of them might be, but they are divided into three distinct classes. We don't know which belongs to which class, or which, let's say they belong to distinct types, cell types. So we don't know which cell belongs to which type, and but we are trying to find it out based on some information that we could extract from each of the cells, right? So so what we do is we try to extract some information out of the cell, right? And so that we are able to predict which cells are similar to each other and which are not similar to each other. The similar ones, we can group them together, right? So what we do is, in order to gather some additional information from the data, we will sequence the mRNA, and we'll get the genes from that cell which are active. So just this is just one common operation that is performed in biomedical research. So it's we are just doing sequencing, RNA sequencing. So we get information about all these genes of these different cells. So now, as you can see, we have sequenced information of 9 different genes, and in row and columns we have all the different cells that we have, right? So this becomes our data set now. Now, as you can see in this data, we don't know which cell belongs to which class. So there is no label, there is no type in the data set. That's what we are trying to find. Like, how can we cluster these cells into the same type, right? So this is the gathered data that we have, and now we are going to perform some kind of clustering or some kind of analysis on this data in order to make sense out of it, right? So let's move forward. So let's say I want to compare two distinct cells, right? Out of all these cells that I have, let's start with a basic problem. We're comparing two distinct cells, right? So as you can see, we have subsetted the data over here to just have information of the gene information of two cells, right? Now what we do is we plot this information out on a graph so that we can see how the gene information, how each gene information of one cell differs with the other, right? So now once we start plotting, we see, so this is a y-axis is cell 1 and x-axis is cell 2. As you can see, as cell 1, as the value for cell 1 increases, the value for cell 2 decreases, right? So this kind of a relation is called an inverse correlation, where when the value of one variable is increasing, the other is decreasing. So we say that they are inversely correlated to each other, right? So this is how you can do a basic analysis between two distinct cells. You plot the information of both the cells that you have on a plot, and you can see how they are related to each other. But what if I have 3 cells, right? So therefore, for 2 cells, it is easy. I make a 2-dimensional plot. I'm able to plot all the data points and verify how they are related to each other. But now, what if I have 3 cells, right? So in case of 3 cells, what I could do is I could actually draw a y-axis and then do some plotting. But then again, it is difficult to visualize, and as you go into 4 cells, 5 cells, 6 cells, then visualizing it in our regular 2D sheet of paper, it's going to be very difficult. So what we can do is we can plot 2D plots, right? So what we can do is we can plot 2D plots of different cell combinations. So in a given plot, you compare only 2 cells, right? So if you have 3 cells, you can see here we have 3 distinct plots. Cell 1 is compared to cell 2, cell 1 compared to cell 3, and cell 2 compared to cell 3. So here you see an inverse correlation. Here you see a positive correlation, again inverse correlation. So that is fine. Okay, so now in case we have 3 cells, we can have 3 plots. But what if this number goes larger? What if we have 1,000 cells, right? We cannot make those many plots, like if you have a high number of cells, like essentially you are you are making 2D plots for each combination. So that will give you like n into n minus 1 by 2 number of plots that you will need to plot in order to reach in order to so these many distinct plots you will have, and then how will you analyze those plots, and it's going to be very complicated task to perform, right? So to avoid this, we do something called as principal component analysis. So what we try, and the essential idea of principal component analysis is, if you have very high dimensional data, you are trying to project that information down to lower dimensions, right? You're trying to project that information down to a lower dimension where the variance in the data can be explained using a principal component, or you can say that you essentially you're creating a new feature. So you have 100 different features, right, in your data set. What you're doing is you're projecting the information from all that features down to one feature, which is your, let's say, principal component one. And that information, that component will represent, like it will represent, let's say, 60 to 70% predictability of your data. So there will be some information loss, of course, because you are projecting from a higher dimension to a lower dimension, but still that gives you a very good rough idea of how your data can be clustered and visualized in a lower dimension, right? So that is what principal component analysis is all about. Now, uh, so basically so as you can see here, I took my 10 dimensional or data, or whatever n dimensional data, I plotted and I projected it down to two-dimensional Cartesian system, right? And you can see that each of my data points, I was able to cluster them. I can now visualize it and see it, that okay, so I'm able to cluster the data based on my projected information. So in 10D, it is very difficult to do. In 2D, with simpler with projecting in lower dimensions, it is much easier to visualize as well. So that's what principal component analysis essentially does. One important thing is, so so first feature, right? The first feature that you project on. So you could project your information, your n dimensional information can be projected down to as many dimensions as you want. You could project it down to 1D, 2D, 3D, whatever, right? Now, up to n dimensions. So the n dimensional data you could essentially project down to from 1 to n dimensions. But usually, one basic rule of PCA is that the first dimension will explain the most amount of variability in your data. The second dimension will again explain some lesser variability than the first dimension, and then the variance that is explained by further and further principal components starts getting lower and lower. Now, what do I mean by that? Uh, is there a question?
Yes, Mr.
Yeah.
Prashank.
Yeah.
You told about the variability, that is the
Uh,
first dimension variability, second dimension.
uh,
What that mean? Can you more elaborate on those things? That is, what is first dimension, what is second dimension?
Yeah,
Uh,
so that we will come to that, but for now, just assume that it is. So we will come to that once we get into the
okay.
nitty gritties of the algorithm. For now, I am just explaining it so that you understand, you get an intuitive understanding of how the algorithm is working, right? And then we will move forward as I explain the algorithm completely. Then when I start moving on to the to maybe how all these things are calculated, then you might understand. Then you will understand what do I mean by variability between between all these components. But okay, but What I mean is, so let me give you a rough overview of what I mean. So what I mean is, so when I say that principal component one has explains your data much higher than principal component two, right? Or shows or explains more variance than principal component two. What I mean is that, as you can see here, we have plotted three distinct clusters, right? So since we have plotted these three distinct clusters, you can see that, let's say, distance between this point of the extreme point of this cluster and this cluster is, let's say, it's x, right? And from this cluster to this cluster is also x, right? So both the clusters are, let's say this is cluster A, cluster B, and cluster C, right? Both the clusters are equidistant. So A and C are equidistant from B. Okay. But what this means that principal component one explains more variance or variability in the data. What it means is that B and C are much more different, are much dissimilar to each other than A and B. Because A and B lie on the second principal component that explains less variance, and principal component one explains more variance. So even though they are equidistant on the x and y axis, the data that is present on the x-axis is much more dissimilar, or these clusters, they share less similarities between each other than these two. So I hope that gives an intuition of what
Yeah.
variance is.
Thank you.
Okay. Yeah. So moving forward, now we come to how PCA works. So let's say we take two genes, right? Information of two different genes. So to start with, let's say we plot one-dimensional data. So for gene one, what I'm doing is, for each cell, I am just plotting information, right? I'm plotting all the information on my 1D axis. So for gene 1, as you can see, the values for cell 1, cell 2, cell 3 are higher. So I plot them. So they are on the right hand side of the axis, and cell 4, 5, 6 are lower. So we go a little bit on the left hand side of the axis, right? So this is how I can explain this information on a one-dimensional graph. Now I have cell 2's, I have gene 2's information as well, right? So now what I will do is I will try to plot both of them simultaneously, right? So I will plot gene 2's information plus gene 1's information, right, for each of the cells, and then I get a 2D plot that looks like this, right? Now this, what I'm trying to explain now, is how principal components are calculated. How do we actually get those principal components, right? So we have two genes, we plotted 6 cells information, we get a 2-dimensional plot, right? Next thing what we do is, we will try to calculate the center of this plot. So what do I mean by center? You simply take the average, right? You simply take the average of all the x-axis, right? And then same you do for y-axis as well. So what you're essentially doing is, for each data point, what is the average of x? For each data point, what is the average of y, right? That value, once you get, you plot it. Let's say this is the point, right? Now, once you do this, what you do is you shift your axis so that this average point that you have calculated becomes the center, right? This becomes your origin. So now, as you can see in this diagram, we have shifted the axis in such a way that that our average point that we calculated has become our origin. Now, what we'll try to do is we'll try to fit a line to this data, just like a regression problem, right? So we will try to fit a line to this data, and then we did, as you can see, there is this red line as, oh, sorry. This red line has been fit to the data, which is basically, so it is not a regression line. To be clear, it is not a regression line where we are minimizing the distance between the residual distance between the line and data point. So as we learned in linear regression. So this is not that. So, but I will explain what this is and how this is computationally better than linear regression. But for now, let's say that we are fitting a line to this, right? So in this case, rather than minimizing the distance between the data point and the line as we do in regression, we are actually calculating, what we are doing is we are maximizing the square of the distance between the projection and the origin. Projection essentially is the distance from the origin on a unit vector. We'll come to that, but we are not minimizing, but we are maximizing the squared distance of that data point from the origin, right? And once we get that line, right, once we get this line is called our principal component 1. This line is now our principal component 1. And then from origin itself, we draw a perpendicular to this line, and this becomes your second principal component. So principal component 2, right? And of course, you see this is two-dimensional data, so you could only have two components. Now, as you increase the number of dimensions, say we had a z-axis as well. So of course, to the second and first principal component, you could draw another orthogonal, which will be your third principal component. So that's why I earlier said, like, if you have n dimensions, you can project the data from 1 to n dimensions, because in each, so as you can see, if even in 2 dimensions, I can make 2 principal components, right? So similarly, in n dimensions, you could make n principal components that where each component describes the variance in your data. Like it essentially tries, it explains the information in your data, so the predictability of your data. So more the data that lies along the first principal components, more the expressivity or more the variance, right? So, okay. So now, now that we have plotted, we have both the principal components, right? Yeah, question?
Uh, Sorry again, Prashant.
Yeah.
Actually, I do having the query. You define about the variance of the principal component 1. So over here is variance, you mean to say the whatever data points are belongs to PC1. Okay. Variance is belongs to those one, or if we having the PC1, PC2 or and PCN. So variance between the PC1 and PCN.
No. So what I mean by variance is between all the features. So for example, you have 10 different features in your data, right? Now, one of the features, let's say feature X1, from X1 to X10, you have 10 features. X1, when we say that X1 has high variance, it means that each data point, so when you take the mean of that particular feature, each data point, when you subtract it from the mean, right, and then you sum it up, it's going to be a high value. So the data is not distributed closer to the mean. Okay, and when you have low variance, means that all the data distribution is closer to the mean. So having a high variance in machine learning usually means that the data has more predictive properties. You know, that if everything is just the mean, right? Example, if all data points have value 5, how will you actually be able to predict if suppose a new data point comes in? How will you use that information that if everything is 5 and some new information comes in, then essentially you will just be predicting the next value also as 5. So your model is not highly predictive, since the features don't have that much variance in them. So that's why it is in ML or in basic statistics as well, the features, that have the highest variance usually are the most contributing factors to your ML model, right? So what PC1 does is, out of these 10 features, right, which it will emphasize the features, it will the projected information from higher dimensions to this PC1 is going to be it is going to be projected in such a way that PC1 will store the most variance. So it will have the most predictability between your data points. And then once you make an orthogonal to this, the perpendicular PC2, that will explain the next amount of variability in the data. So that's why PC1 explains the highest variability in the data, means that PC1 is responsible. So this component, if you actually use it to train your ML model, this will be the most beneficial or most contributing feature for your ML model. So that's why PC1, when I say it has the highest variability, I mean that.
Okay.
Does it make sense? Okay.
Yes, yes.
Okay. So now what we do is, once we have both the principal components, what we'll do is we'll rotate the axis in such a way that the next step now is to project. So whatever data points we got, right? So whatever data points we got from here, in this case, let me just clean it up a little bit. Yeah. So whatever data points we got from here, we will project the values on individual axes on PC1 and PC2, right? So what we are doing is, from a higher dimension, we are project. So since in this case you can't really make it out, because from two-dimensional data we are projecting it to 2D. So it won't really make much sense here. But assume that there is another gene 3 as well here, right? And that information also I am projecting on PC1 and PC2, right? On these two axes. So what I'm doing is, I am from three-dimensional data, I am projecting it down to 2D on these two axes, right? Now, once I project it down, so X and Y, so if we plot it, it will look something like this, right? So each point was somewhere here on that three-dimensional plot. And now we have taken the projections on PC1 and PC2. Now, what we do is, once we have this, we will plot those individual points again, right? So now, so basically, these projections I am replotting down into a lower dimension. So now from 3D, which was 3 genes worth of data over here, that you see here, X axis, Y axis, and Z axis, what I did was, essentially, I brought it down to 2D, right? And this is called singular value decomposition, where I have projected it to a lower dimension, reconstructed. And now, so maybe if if in this 3D plot, if it was difficult to see those clusters, and it could have been a 10D plot, right? It could have been a 10D plot, and it could have been very difficult to see how the points are clustering. But now, once I projected it to lower dimension, and since these two components are explaining the most amount of variability in my data, I could say that okay, these are the kind of clusters that are being formed. So this is called singular value decomposition, and this is how you. So you could also plot a third principal component. That is perfectly fine, but then again, that will be a less contributing factor to your final variability or variance that is explained by each of these components. So PC1 will be highest, 2, 3, and then keeps on reducing till it goes to n. Now, as the number of features will increase, principal components, the number of possible principal components that you can create can also keep on increasing. So it is usually very difficult to visualize, but the first two to three components, see, the first two to three components are able to explain the maximum variance of your data set. So usually in practice, we stick to first two or three components to see how the data is behaving, because the lower components, they are actually encapsulating the less contributing features in the data. So if even if you ignore it, although there is a little bit of information loss, even if you ignore those, it is fine. And that's the trade-off that you are making when you are projecting to a lower dimension, right? So that is what is happening in principal component analysis. Now, let's move to how. So let's move to how we are fitting that line, right? So that also we need to understand. Like it's not linear regression that is happening here, right? So what we are saying here is, sorry, what we are saying here is we are rather than minimizing the distance between the data point and the line, in order to fit this line, we are maximizing the squared distance between the projection and the origin, right? So what that means is maximizing the squared distance means that choosing a direction. We are trying to choose a direction such that when data points are projected on it. So, for example, I choose a vector such that when I project all my data points on that vector, the sum of the squares of these projections, so the sum of the squares of these projections are going to be of the highest possible magnitude. So I'm trying to maximize the sum of squares, right? So essentially what I'm trying to do, I could simply say that I'm summing over all my data points, right? And squares. But there is another thing, since we care about the direction, because we want to find the direction of the vector. So let's say we have a unit vector that is multiplied by this, right? So I have all my data points. I am summing over all the data squares projected on this unit vector, right? This is what I'm trying to find. Now this, I can also rewrite it as this unit vector transpose of this. So and this E is called the covariance matrix, right? So essentially this data we have transformed it into a covariance matrix. What is a covariance matrix? We'll come to that. If covariance matrix is basically a matrix that is able to explain the relationship between different features within the data. So it's usually what it will do is, so for example, you have n features in your data. 1, 2, 3, 4 goes to n. 1, 2, 3, 4 and goes to n. Okay. So what covariance matrix stores is, for example, let's say at row 1 and column 2. So these are two. So this value that is there in this matrix, it will tell me how feature 1 is related to feature 2. So if this value is highly positive, then it is a positive correlation, which means that if feature 1 is increasing, feature 2 will also increase. And if suppose it's a negative value, let's say 2 and 3, here I have a highly negative value. This would mean that feature 2 and 3 are negatively correlated. Positive and negative correlation we saw earlier, like if one is increasing and the other one is increasing, it's positive. And if one is decreasing while the other one is increasing, it's negative correlation, right? So that is essentially what, so all this information using some linear algebra can be transformed into this, where you take, we are taking the transpose of unit vector, multiplying it by your covariance matrix, and then again with your unit vector. So this is the problem that we are trying to optimize on, right? So in linear regression, what we are doing is Let me clean this up a little bit. Sorry. In linear regression, what were we doing? We were just simply minimizing, right? Minimizing on all your data points, and this same equation that we saw a couple of days ago, mx plus b squared of errors. You're trying. This is your cost function. You run gradient descent on this, and you come up with the optimal value, right, for m and b, and that's your line. But in PCA, what we are trying to do is we are trying to find one unit vector, one unit vector based on which based on which once the data is projected, the it is maximizing the values of your covariance matrix, right? And unit vector, of course, is any vector that's magnitude is summing up to one. So in 1D it is just one. In 2 dimensions, it could be like anything. Like so, for example, 0.6 and the absolute plus 0.8 square is going to give you one, right? Square root of that is going to give you one. So that's why. So unit vector is basically a vector whose magnitude is one in any dimension. So, but why are we taking unit vector? Why are we not taking some vector with a higher magnitude? Because we don't really care about it. What we care about here is the direction. That's all we care about, the direction of the component. Once we get the direction, the vector can be scaled as we want. So for now, even if we take the cost function could have just unit vector, that is completely fine, right? So now what we are trying to work on is to maximize this, right? So rather than linear regression, which where we have to minimize and we have to optimize parameters by trying different parameters, using gradient descent, coming to an optimal value, right? Here we don't have to do that. We just have a maximization problem, where you have a unit vector, you have a covariance matrix, and you're trying to maximize this value. And one thing is that this is equal to 1, right? This is a standard eigenvalue decomposition problem where it has a closed form solution. So you don't really need to do gradient descent to find optimal parameters. You could find the eigenvectors for your covariance matrix, and those eigenvectors are your principal components. So the computation here is very easy as compared to gradient descent. Okay, and so that's why PCA calculations are computationally much more efficient for fitting this data. And yeah, that's the core idea to fitting the line in PCA. Then, of course, drawing a perpendicular to that is not really that difficult. What else? I think another thing to know is, so maybe rotation, right? So once you have this, you have plotted this mathematically, how do you rotate the axis? While then this is an implementation detail, like once you have the principal components, which are the eigenvectors of your covariance matrix. So you have PC1 and PC2. What you're doing is you are simply multiplying these principal components with the actual data matrix, which is your X. So your input matrix, which has by the matrix your on X by PC1 you get the X, and PC2 you get the Y axis. So that's how rotation happens. And yeah, so that's principal component analysis. And I think we can now move to the next algorithm, which is k-means clustering. And if anyone has any questions on principal component analysis, please feel free to ask. All right. So I will move on to k-means clustering now. So Well, we yesterday we learned K nearest neighbors clustering, right? In K nearest neighbors clustering, what we saw was that you you don't really need to train your model or anything, right? You just have to plot all the data, whatever new data point comes in, right? You have you sorry, I'll just try to draw it, right? You have to just plot all the data, right? Let's say you have uh, you're plotting the data like this, right? Now, whatever new data point comes in, let's say this data point, right? Let's say this is the new data point. Whatever new data point is coming in, you simply take the top k nearest neighbors to that component. So let's say my k is 5, right? K is equal to 5. The top 5 nearest neighbors are these, right? I I say okay. So out of these 5, let's say this is class A, B, and C. A belongs to two data points belong to A and three data points belong to C. So this new data point will be classified under class C. So it will be a K nearest neighbor clustering. It is that simple to compute, where you just based on the distance that you calculate between different points, you end up with the class, the majority class of from those k values that you sampled. K means clustering is a unsupervised learning technique. Now here you don't have the classes, right? In this case, in this particular case, you had green, yellow, blue. You had the colors to tell you what point belongs to which class, right? So that's why you can sample it and take the majority class and assign that label to the new data point. Now in K means clustering, you can't really do that because you don't have the classes of your data. So here what we'll try to do is we'll still try to cluster the data based on distances, just purely based on distances between the data, right? So this is one of the most commonly used technique for clustering similar data points, right? And basically the algorithm is taking a parameter k, and this value is the number of clusters that will be forming using our data, right? So in order to explain this, I'm going to start with a very simple example, one dimensional example on this axis. As you can see, I have a bunch of data points that have been plotted on one axis, right? Now, by looking at it, you can kind of say that okay, these three are kind of forming three distinct clusters here, right? So how do I actually come up with an algorithm that can find these clusters, right? So let's see how it works. Let's say I start with k is equal to 3. I assume that for now let's assume k is equal to 3. We randomly select three distinct points in the data. So on this line, let's say this is 1, this is 2, and this is 3, right? So these 3 points we have selected randomly on my x-axis, right? Now we take each point in the cluster, right? So basically each point in the data set we will see, and we will basically calculate the distance between these random points and that other data point. So the point that is nearest to 1 will be classified under this class. The point that is nearest to 2 will be classified under that class, right? Point which is nearest to 3 will be classified under that class. Okay. So now once we do that, we see that it looks something like this, where this has been classified as class A, this is B, and this has been classified as class C, right? Does not look correct because highly skewed. C class could be broken further down into two distinct clusters, but somehow we have stopped here, right? Finally, we assign the points to each of these clusters. Now, next step is we will take the midpoint, or we will take the average of all the values within the cluster. Okay. So what we do is, so here we got all these clusters, right? 1, 2, and 3. And here we take midpoints of each of the values in the cluster. So now we come here. This is first, second, and third cluster, right? So these are the centroids, the A, B, and C. Now, considering these are the cluster centers, we will again do the same process of calculating the distances between each point and the cluster center, right? We do that again, and we again got the same values because nothing much has really changed here, right? So this is again same, right? This is same since all the data points lie somehow they are lying around around the same area. That's why our algorithm has stagnated at this point. We can't optimize any further because uh, anything else you do, you will always end up with these midpoints. So if you have a loop which is recalculating the centroids after each time you update, uh, after this point you will just end up with the same centroids again and again. So this is where your algorithm has stagnated. These are the three clusters that you found. Now, of course, these are incorrect, but incorrect, like they look incorrect, but how do we optimize on that, right? So now we see that there is no change in the cluster centers and the assignment of these points. Thus, what we do is we are terminating the clustering process. Now, it doesn't seem to be a very good classification, right? But what we will do is we'll try to learn from this. Here we will calculate the variance in the data, and as I explained earlier, what variance is the distance from mean of different data points, right? The distance from mean of different data points will give me the variance in the cluster, right? Now, in order to optimize or to find the optimal clustering, there has to be least variance in the data, right? So that kind of tells us that okay, this cluster is relatively stable, that the distribution is kind of around the same area. That's what we want, right? We are trying to form clusters. We are not trying to increase variability in the data here. Here, in this case, what we are trying to do is we are trying to form clusters within the data. So what we're trying to do is we are trying to reduce the variability. So in this case, first we will calculate the distance from the center of the cluster to each data point in for each cluster, and then we'll sum it up. So essentially, you're calculating variance where you are summing up some the differences in these values. So let's say for each, let me write this here. So variance would be, I'm summing up X such that for each class, I am simply taking the magnitude of difference from mean and squaring it, let's say. And this will give me my variance. Of course, for variance, you have to square, but yeah. So this is giving you the variance. And higher the variance, worse is the clustering. Okay, because the data is more distributed here and there, and we don't want that because you're trying to cluster the data, right? So what we do now, next step is to rerun the whole process again, right? But this time when you start with different initial points. So in this case, we started with random initialization. We came up to centroids. It did not optimize any further. We stopped, we calculated the variance, we got a high value, we restarted the process. Okay, we restarted the process. This time, we we chose other two distinct three new points, which are again chosen randomly. But this time, as you can see, so first in the first iteration, we see that this point, all these 3 points are assigned to this cluster, to this centroid. Now these 2 points are assigned to the green one, right? And ones on the left are all assigned to the blue one because those are the closest to blue, right? So now once this is done, the next step is I will take whatever is assigned to blue, right? I will take the average. So these 4 points are assigned to the blue cluster. I will take the average, it will come somewhere over here. So my average came here. Now, same for the green one. I will take whatever is assigned to green, I take the average somewhere, let's say it came somewhere here. And same for the orange one, it came somewhere here. Now it seems well classified. Now, if you take the variance for this, if you calculate variance again, you will come up with a value which should be lesser than the one that we saw in previous case, right? And that's the idea of k-means. You can't essentially narrow it down to one form of clustering, like one, but like in just one or two iterations, you can't say that, okay, these are perfect clusters. You have to keep on clustering the data again and again to see the variance, and you have to come up to a point where you are getting the minimum variance, and that's your optimal clustering, right? Um, and that's once you get that, you say that, okay, your clustering is done. Now, question here is, I chose k to be 3, but why? Right? Like that, how do we choose the optimal value of k? Because initially we did not know like how many clusters can be formed. In this case, just looking at data is kind of giving you a hint, right? That that okay, this might have 3 distinct clusters because there is so much gap between the data, but this might not always be the case. Then how would you choose the value of k, right? So in order to choose the optimal value of k, what you do is you take one value of k, you calculate the optimal clustering, right? You calculate the optimal clusters for that value. You calculate the variance and you plot it, right? Then for k is equal to 1, for k is equal to 2, for k is equal to 3, you plotted variance, then 4, and then 5, right? Now in this case, you will see that for k is equal to after k is equal to 3, the reduction is variance is not as much as it was for k is equal to 1 and 2, right? From 1 to 2, there was a big jump, 2 to 3 big jump, but then it wasn't that much. So this is called a typical elbow plot, and this point is where you're kind of stagnating the value and not much change is happening after that. So after this point, if you increase the number of clusters, it isn't going to make much change. So what the optimal point to be selected here is 3. So that's so this way you can come up with the optimal value of k using an elbow plot. Okay, and okay, so this was a technique that I showed to give you an intuition in one dimension, right? So how k-means would perform in one dimension, but of course your the data that you are going to be using for when you do your statistical analysis or when you do ML modeling, of course the data is going to be going to have much higher dimensions than this. So in that case, all the same rules apply to higher dimensions as well, but you just have to do it individually. So what the calculations that we did on x-axis, the same thing you have to repeat on y, the same process repeats again, essentially calculating the distances again, right? And what are the metrics we used? So in this case, most of the times you use the Euclidean distance that we saw yesterday. So simply you subtract the value of like the magnitudes, square it, and the root, and sum it over all the values and over all the different dimensions, and take the square root. That's a Euclidean distance between 2 points. Similarly, you could be using Manhattan distance or Minkowski, whatever is suitable for that particular problem. And yeah, and the same thing can be scaled up to n dimensions. So you can scale it up to as many dimensions as you want. And that essentially uh, completes K means clustering. So we saw that how even without having the label for a particular data point, right? We in both these algorithms in PCA, in principal component analysis, and in k-means, we did not have any target, but we kind of were able to cluster the data together, see the relationship between different data points and how they are related to each other, and then put them and then say that okay, maybe they belong to the same class, right? So this is what happens in unsupervised machine learning, and these two are the most commonly used techniques in unsupervised ML. I think with this, I'm open to questions, and we can. I think we can stop here for today. That will be our uh, unsupervised machine learning, and tomorrow we will go into some basic neural networks and deep learning algorithms. So yeah, any questions? I'm open for questions.
Once again, Prashant,
Uh-huh.
uh, uh, as we having the data points, okay, so PCA, as we discussed, that is a variability is a more good thing. But if the same data I do having for the k-means also, so the variability itself affect my first thing, that is a centroid. So how to manage those kind of scenario? You just avoid that data point, or you have to manage somewhere in a nearby or somewhere else.
As in the algorithm will take care of that data, like of that data. So you are saying that if if the variability is increasing, how do you manage it? Is that what
Yes,
you're asking?
yes, 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 yes.
Yeah. So the essentially that's the reason why you are doing multiple iterations with random initialization. So the whole point of doing this is that you can't make out from the data how clusters will look like, because the data see, looking at this plot that you see on your screen, it is easy for us to say that okay, there are three clusters that could
Yes,
be formed, right? So if one of the point is an issue, how do I handle it or something like that? But that that is not the case when you have 100 different features. So if this axis, this 2D axis, are converted into a 100-dimensional axis which has 100 features plotted on it, you visual references are not going to help you in figuring out how clustering will happen. So that is where you have to really rely on the algorithm and the math behind it to converge to the optimal clustering. That's why you have to restart randomly again and again using different initialization, using different points of initialization, and eventually and calculate variance at each after each at the end of each clustering, at the end of each iteration, and then at the end of it, let's say you clustered 1,000 times, the iteration in which you got the minimum variance is the one where optimal clustering is happening. Maybe there is a better way to do it. For that, you will have to maybe do it 2,000 times or 10,000 times to come to that particular point, or to reach that particular centroid. Does that
okay.
make sense?
Yes,
Yeah.
yes.
Okay. All right. So So, yeah, any other questions?
Hi, Prashant. Pawan here.
Hey, hi, Paul.
Ah, in this K-means algorithm, you mentioned that elbow graph
Yeah,
is it, and also previous section last one day I think you
yeah, there
mentioned
was
that
this.
the elbow graph is important. So
Yeah.
why it is important things in the machine learning algorithm?
So when it comes to K means and the same elbow graph, if you remember, it came back in K nearest neighbors as well. So this is where, so when you're trying to again, so see, we are trying to find what are the optimal number of clusters that explain the variance of the data. So we are trying to come to that optimal value. So when we are clustering, you in any kind of clustering technique, you will always see this elbow plot. Elbow plot always comes up
Mhm.
because if you if you if you take lesser number of clusters, right? So for example, if you take a lesser number of clusters than what you have. So, for example, we take two, right? Let's say we take two clusters. So, probably this data will be clustered something like these into these two clusters. Now, see, you can see that they are not uh, they are not very efficiently clustered because there is still a lot of variance to be explained. Now, if I move it to three, then my net variance, and that's what we are trying to do. We are trying to explain the variability or the variance in the data, right? So once and if we go above this, so you're trying to just find the optimal parameter that can, in the best possible way, explain the variance in your data. So this parameter, if and this is one way to find it. So essentially, what you're doing is you're just finding the like how your variability or variance in the data is changing as you increase the number of clusters. Now, of course, it will still keep on increasing if you increase, so it will always keep increasing. If you increase the number of clusters, if you go to 4, 5, 6, more the number of clusters you add, the more variance in your data will be explained. Because that many centroids you will have. So more the number of centroids you have in your data, the lesser will be the distance between the centroid and that data point in the cluster. So lesser will be your variance. So uh, you will this will keep minimizing and stagnating. Similarly, in principal component analysis as well, right? So first component explains certain amount of variability in your data, let's say 70%. The second one explains 20%. Third one explains 10%. No, not 10, let's say 8% or whatever. And then as you increase the number of components, principal components, it explains more and more from your within your data. But the optimal point is you don't really want to overfit the data, right? You want a generic idea of how you would classify a certain new data point. So if suppose I am getting a new data point over here, right? I want to optimally classify it rather than having a high number of clusters that let's say one cluster is this, then one cluster is this, one cluster is this. I took so many centroids. Now my variance is much lesser than what it was for three clusters, right? But then the problem is uh, the problem is that the new data point that is added, how do I, like, it won't really generalize to the overall data set. So if all these belong to the same class, I'm kind of forcefully breaking the class down into further classes, which I don't want to do. That's why we use these techniques like elbow plots to kind of come to that optimal value, that what is a good bias variance trade-off. Again, bias variance trade-off here. What is a good point to settle to, so that I can generalize the best to this data. That's why we use this elbow plot, and that's why this point explains the most. That's why this inflection point, we say that usually you choose that value. Of course, there are a lot of other techniques, and nowadays people have started saying that don't rely on elbow plots. Maybe sometimes they don't perform very well on certain types of data. So that's a completely different argument. But in general, traditionally, elbow plots have been used to find the optimal number of clusters. So yeah, any other questions? Pawan, does that explain your question?
Yes.
Okay.
Thank you, Prashant.
Yeah. Any other questions? All right. So I guess we can stop here. Okay. Uh, Hello, sir. You're there in the call. Can we stop for the day? Okay. I stop the screen share. Okay. I guess we can stop. All right. Thank you, everybody. See you tomorrow. And if you have questions, please put it on the group chat. I will try to answer there. Yeah. Thank you.
Thank you, sir. All participants, today's and tomorrow's feedback link is only shared in Google Meet link, Google Meet chat and YouTube chat. Please feel